Okay, today is October 11th, 2023. So far, we have reviewed most of our manufacturing process of composite, including thermoset and thermoplastics. Well, we will certainly review again whenever needed. Today, we will start to cover some basic mechanics of the composite. This is generally called the classical laminate theory. We will briefly go through that. Okay, but still, as a the introductions of the composite materials, we like to briefly review several slides. We've been already discussing many features of the composites, but just for the purpose of review again, I will go ahead with using a different slide. My screen is well shared, my desktop. You guys can see my slide.
Yes, sir.
Okay.
We can see.
Again, the let's say structure of composites, meaning that structures can be any structures. The figure show is the airplane, but could be a wind turbine blade, could be some automotive, or could be some pressure vessel, anything. That is called structures. Now structures is made of composites. So composite materials are widely used in aerospace structures and etc. And there are several forms of the composites in general. There is a different shapes depending on the fibers and resin system. We can have a different name. And A shows the particles, composite particle reinforced composite, and B is the a little chopped strand or short fiber, and C is the unidirectional, or this fiber here is the continuous, and D is a laminate. Laminate means that consists of each ply, and each ply can be a long continuous, or sometimes some particle or short fiber. And E is the woven fabric. We several times reviewed this woven. Each woof and webbed represent is from the toe. So E is the well, it just say fabric, but the woven fabrics, and F is the two skins. With each skin will have a laminate, but mostly in the center we have a honeycomb structures. And honeycomb structure is to support some especially the bending load, because the bending stiffness is well above the regular structures. Okay, this is the structures of composite, and can be composite can be many different forms. And now fiber volume fraction definition is very important. What does it mean, fiber volume fraction? Well, again, the fiber usually means that long continuous, but as you can see, the particle can be also a reinforcement and short fiber, etc. So we generally call them reinforcement, or we just can call them fiber. Okay, fiber doesn't mean just a long, but fiber in this case represents a particle reinforcement. So, for example, we have to pay attention to a volume. Volume means a geometric fraction. Sometimes it can be represented by the mass fraction, and sometimes a volume fraction. This is a long continuous fiber in the resin, and this geometry, usually the fiber volume fraction can be 60%. And usually if we increase the fiber content, the modulus of elasticity will increase, as shown here. And broken fiber, well, this is just a list of several issues. So each topic or each issue is not quite related, but just some issues in composite in general. And broken fiber means that this shows the long continuous fiber, but each fiber or filament can be broken during the manufacturing defect, or during the fatigue load, or some manufacturing process. So one of the fiber can be broken. Now the main point is that this broken fiber is supported by the older resin system by shear load, and then this load is carried by the adjacent fibers. That is the main feature of the fiber reinforced. So locally, we need to visualize what will happen to broken fibers. Easily the fiber can be broken, but we don't worry much because there are so many fibers surrounding one fiber, and the most of the load is just the transmit through a resin, and then other fibers can support load. And another issue will be a laminate with a hole. If we have a hole and then under tension, the laminate can be 0, 90, or others. And the geometry can be diameter and with respect to width of the specimen. So usually D over W. And this is the shows the stress concentrations. As you can see that if D equals 0, this is there's no notch, nothing, it's just a flat. But if we have a D hole, then as you can see, stress will concentrate. This is a very common behavior of the general materials, and it happens in composite materials as well. But composite material, this notched behavior can be very severe because each lamina in a laminate can have a different materials. Now, another issue is the failure under compression. We already reviewed the behavior of compressions of the carbon fiber. And under compression, the fiber cannot support effectively the compression load. The failure mode and the deformation mode can be very complex, but in general, under compression, each fiber looks like the one column, and you can easily visualize that this column cannot well support the compression load in fiber-wise. So there could be some defect initiated in the resin system by shearing mode or some opening mode. Okay, so this is the we can call micro buckling, but also a lamina to lamina. There can be a delamination, and this can be called the buckling can be caused by the delamination or some shear load associated with a local buckling behavior. And this is the honeycomb structures, and this honeycomb is attached, but the skin can be separated or compressed locally. There can be some issue there. And this is and the residual stress can be generated between the fiber and resin system because you know, the thermal curing process in resin is quite different from fiber. So when cured, the resin usually not shrink compared to the fibers. So as a result, there can be a large amount of residual stresses. So this can be another source of damage. We need to understand this behavior. And the fibers, there could be many different types of fibers. Carbons, so there's a spelling error. The carbon and boron and Kevlar and e-glass. Usually the carbon is one of the best fibers. As you can see, stiffness is good and strength is good. Where usually the carbon is a little stronger, like the reaching 4,000 or even 5,000. So this figure has some, it's not quite correct. The carbon can reach this much. So it can be, strength can be 4,000. 4 giga means 4,000, and or sometimes 5,000. Or it could reach the 6,000 as well. And the high modulus carbon means that this stiffness can be even higher, usually 250 or 300, but it can be even higher. Now we have a Kevlar and e-glass. E-glass, the stiffness is low and strength is low relatively compared to carbon. But the good thing is with glass fiber is the much larger failure strain. That is the important features. So the I would say this is the this much, and this is the carbon. Okay, well, there are some way to measure the fiber and epoxy and rigidity by the compare between the fiber and resin system. The Young's modulus, stiffness of the fiber is much larger than resin system, and deformation compatibility and deformation compatibility in Poisson's ratio. So each layer will attach together, and then this will have some Poisson's effect. Under tension, any material will have a shrinkage in transverse direction under tension load. That is called the Poisson's ratio. Okay, well, I just share with you some issue which we can easily find from internet. Now here, I like to emphasize the two most important behavior of the composite. before we start to study about the mechanics of the composites. Okay, two main issues. One is the fiber and resin. As you can easily see that the fiber, let's compare the fiber and the resin. The stiffness, okay, the stiffness will be about fiber stiffness, I would say 250. This is the stiffness, and I will say strength. So the fiber stiffness, well, let's consider carbon and resin. The typical is the epoxy resin system. So stiffness of epoxy resin is about the 3.5 gigapascal. And the stiffness of the carbon fiber, I would say 220 or 50. I would say just 220 gigapascal. I hope you remember these numbers. It's a very important number. You have to remember them as a reference so that you can easily judge other material property compared to carbon and epoxy. Now, strength can be like the 5,000 megapascal, and epoxy strength will be about I would say 70 megapascal. So usually stiffness we are using the gigapascal, and strength we use the megapascal. And now the failure strain, strain can be easily defined by the strength divided by the stiffness, right? So this will be 5,000 divided by the 220, 10 to the 3, and so on. So you can see that how much the failure strain will be. So fiber, the strain is also very important, as you saw the previous graph. So the okay, I can just write down the number here, not precise number, but engineering sense, this is the number you can remember. So this is like the 2%, and the epoxy resin, you can divide by that about 3%, 4%, but in this case, stiffness and little bit, well, I would like to 3%, okay, including plasticity. So this is the kind of number we need to remember that. Now the very important point is that let's say let's take a look at this strength and how much it can support, and the fiber how much it can resist under deformation. Now, by the stress and strain curve, we can see this is the very high stiffness. So we can draw some stress strain curve like that. And this one is the strength is the 5,000, and the slope will be 2,020 gigapascal. And epoxy resin system is now the stiffness, as you can see, very, very small compared to this. and the strength is also very small. And then there will be some plastic. This is the very typical curve, and this is the slope, and this is the strength. So the fiber and resin system has their own very different material property, but one of the most important point here is that the fiber is surrounded by the resin system, meaning that in whatever we have usually the under fiber direction, this will deform together. So just the cross section, this is a fiber, but keep that in mind. It deform together. Okay, deform together this much. So this gonna be a final deform shape, and this gonna be a initial shape. So the as I said, the most important point of the fiber and resin system is that the fiber and resin, they deform together, meaning that this amount of strain, this strain, either fiber or resin, they deform together. The strain will be the same. What does it mean? In the horizontal axis, strain, no matter how they deform, the strain will be always the same, either this much, or this much, or this much. So at the failure, at the, for example, fiber failure, this is the deformation. So up to a failure, usually the fiber failure, this fiber reaching this much. I mean, fiber, this is the fiber, and this is a resin. And each material will have a internal resistance or some load carrying curve. So importantly, no matter what how much the level, the strain is always same amount. And why is this is so important? Well, as you can see that the fiber is taking over most of our load, and the fiber volume fraction is about 60%. So in composite, 60% of the volume will be the fibers. So whenever the composite is deformed, volume-wise, 60% of the fiber will take over the load, but as you can see, very stiff. Now here, another point I like to mention is that the fiber will be a break. Okay, fiber will break, and there will be some resin outside. I will draw like this. So what I'm trying to say here is that the fiber will carry the certain load according to this much. But the most of the load carried by this is the resin system is by the shear load. So again, if you look at some broken fiber in a composites, you can visualize something like that. Okay, if it's broken, then how the resin is weak, but how can this weak resin carry the load? Okay. How the weak resin carry the load in composites. There is the question we should be able to answer that. So in a big composite material, and there's a very much local, and this can happen very easily, either short fiber and long fiber, always this can happen. Now, this is the I would say the cross sections AF, and now this is the strength. I would say the fiber strength, and there will be some load F. So F will be sigma F times cross sectional area, and the strength, as we just saw that, we can say this is the 5,000 megapascal, and times the cross section of the AF. AF is what? I would say the diameter of the fiber, carbon 7 micrometer. So pi over 4 divided by the 7 micrometer. Okay, this is a micrometer and scale. So anybody can calculate this one. So this is gonna be 5,000 times pi over 4 and 7 scale. The unit is the 10 to the 6, and the micro is scale. What does it mean? So one over 1,000 means that divide by 10 to the 6, right? There's a scale there. So this one, and then this. So what is that? About simple this much Newton, right? Something is wrong. Too high. Is that correct? Too high. Tell me what is wrong here. That's right. This is not the 10 to the 6 micrometer, is already 10 to the 6. So this is gonna be 12. Right? So this is what? 0.2. Newton. Well, that looks too small. Six. I think this is okay. Now, so each fiber, if it takes the 0.2 Newton, or you can say that this is what? Okay, well, just a 0.2 Newton, this fiber will be broken, or some will failure. So this is a load carried by the fiber until the broken. Each fiber, just one fiber. But the point here is that the fiber and resin is the bonded, and now all the load, this much load, is carried by the resin system. Now, let's consider this is now this length. See, point here is this is all carried by the, I would say, the shear load, shear stress. So shear stress times this is the, I would say, length, and times 2 pi r. This is the r is the 7 micrometer. And here the length L can be really large. So trying to say that this is the fiber load, but the fiber, the resin is the tau times the L times 2 pi r. Okay, so well, since this is the resin system, the tau is the shear stress. Let's say shear stress or tensile stress or tensile strength, which is the order of what? Order of 70 megapascal. 70 megapascal. But the point is that this L can be very large. Very large. So I'm gonna rewrite this one rather than a number. So F, I can rewrite. This is the sigma F. This is the tau resin times. This is the we had a 4 pi and r scale, right? So the pi and r like this, and then if this is equal, okay, if this is can be equal, in other words, the fiber load is carried by the resin, but the resin is a shear, and over the surface, this is all the surface carried by the resin system. So that is the point here. So the tau F, tau R. Okay, I'm going to rewrite here. L equal sigma F times the pi R, right? So what I like to say is the sigma F over tau R will be R over L, and there is some, there's some constants here. So this guy, fiber strength will be very high. This resin shear strength is relatively small, but this load is carried by the resin system. How? Because we have a long area of the contact area on the surface. So even though this is a very, very large compared to this resin strength, we don't worry. I mean, the way it carry the load by the resin system is this overall area of a contact. And this overall area of a contact is the not just the cross section, but this is length L. You can see that how long the fiber is. So this is the fiber length, and this is the R. And as you can see, this can be small. Don't worry, because this L is very large to carry this much, this high fiber strength. So that's how the fiber and resin system is in harmony in composite. All the load carried by the fiber is carried by the resin system, but how? Well, this contact area between the fiber and resin system. This is the very important mechanics of composites. Okay, so that's why weak resin, how can it carry the load in composite? Or how I would say the fiber load in composite. Okay, so the I think this is the very important mechanics of the fiber reinforced plastics. Again, I briefly emphasize the fiber is very strong in fiber direction. So the strong means that this is the cross section. This strength is very good, but the strength times the cross section will give a certain load. And now this load is carried by the resin and how over the area of a contact between the fiber and resin. And the contact area is very large compared to this R. So even though this resin shear strength is low, the load by the resin or load by this fiber will be well carried by the resin system, since this contact area is very large. So this is what it says in mathematics. Okay, so you don't need to remember anything here, but you just remember all the load are well carried by the resin system by the contact area between the fiber and resin system. This is one of the most important feature of the composite materials. I will say this is the first. This is the first issue. This thing is not well discussed in general textbook. In general, I mean the description of composite material. But from my experience, this is one of the most important in understanding of composite. Now, second issue is that how each ply deform in laminate. Ply we sometimes call lamina. Okay, so lamina, laminate. Okay, laminate means that we have a let's say we have a one ply with a certain let's say just to forget about the composite material for a while, but let's say this is the A material, and another layer will be this material is the B material. And another one, let's say we have another material like the C material. Imagine that A can be any material like the rubber or wood or steel or aluminum. Among any material, you know. B material, same thing. You can imagine any material, any plastic, any metal, anything. And C, same thing. So each one we can call a ply. This is a ply or lamina. This is a ply and ply with a certain thickness and certain material. And this now this is the all combined together. We form a laminate. So now laminate means that these are three materials glued together, and this is the we call laminate. Okay, laminate. So the how each ply, each ply in a laminate. This is the each ply, A and B and C. Each ply will deform in a laminate. Imagine that this is the under a certain load. A load can be here, or a load can be there. Now, the most important point I like to emphasize here is that they are deformed. They are glued together and deformed together. So, regardless of a material property, A, B, C, the point here is that they are deformed together, like this. They are deforming together. So, they deform together. This looks sounds very obvious, but this is the most important behavior of the composite to understand the mechanics. Let's say this ABC material, they didn't glued. This is all three plies is glued. They are all glued. That's why the ABC deform together. But if they are not glued, if we have a certain forces, okay, certain forces together, and this will have their own deformation. I'm gonna okay, this may have their own deformation, right? Depending on how much load it carries. So we cannot say the how they deform, deformation amount. We cannot say when they are individual ply. But in a laminate, they are glued together, they deform together. So regardless of a material property of each ply, they all glued together. In other words, the strain, okay, strain of A or strain of B or strain of C, they are all the same in a laminate. So this is again very obvious, and this is one of the most important feature of the composites. So please keep that in mind, this behavior. And this laminate may have all the strain will deform together or bending together. Bending together means that this will have a certain a curvature, but this is the we call deformation comparability. So based on this, we will continue to study about the basic mechanics. Okay. Now, for a while, we're gonna use some equations, mathematics, to understand the all the mechanics. So please be patient to follow this composites behavior. I'm trying to not to use too many mathematics, but all the behavior better to be expressed in terms of mathematics, which will be very convenient to understand sometimes, and then that's the way we can program that. We can calculate the deformations. And briefly speaking, the composite, now using some mathematics and symbols, we have 3 different materials. And each one will have a certain materials. Material means that carbon, for example, and angle, like the 10 degree or 20 degree, and number of plies. Well, even though one ply that can consist of several plies together with the same material and same ply, but usually you can just consider n equal 1, okay, 1 ply. So means that okay, if the material is the same, we can just consider that each has a different ply angle. Now, what is a ply angle? Well, ply angle means that we have a different fiber directions. So I should have opened the clean slide, but I can delete this. Oops. I can delete them all. Okay. Again, this is the most important slide in understanding of a composite laminate. Let's say again we have a 3 plies. The point here is that they are glued together. They deform together. Okay, so now this laminate can have a certain load and deformation. So this one can extend it or bending, right? Extended or bending. So this is an extension or this is a bending. Extension means that the strain will be the exactly same as the in all plies, since they are deformed together. So all the strains of one ply and first ply, second ply, third ply, the deformation will be the same. Strain will be the same. Now, if this is also can deform, what does it mean deform? Deform means that this laminate will have a same curvature, same bending curvature. So the strain in mathematics, we can say the curvature times this thickness Z. So total deformation of a laminate, whether it's an extension, whether it is a bending, we can always say that uniform strain plus a bending with the curvature and through the thickness Z. So any okay, I will use this one. Any normal strain means that I don't want to confuse you, but it can be this way, or it can be that way, and or it can be this curvature, and it can be this curvature. So this is a one direction. This I like to say this is the one direction or two direction. So one directional strain is the very much uniform, same all of the plane. And then Z is the through the thickness Z times the curvature. Curvature is the this much radius, right? This is the radius R, and inverse of R is the curvature. So any ply means denoted by Z. Z can be bottom, middle or top. Z is here. But we have two constants. One is the a uniform, and this is the radius of curvature. And this the other direction will have the same. The strain will have a uniform strain, and then also curvature. In other words, this can be extended this way, and this can be bending this way. So this is exactly the same. And shear strain is also same. Shear, a little bit different from normal, but mathematically is pretty much the same. So shear means that this plate can have this much the angle change, right? This will have an angle change. See, this was the rectangular, but after shear load, this will have the angle will change. So this is the shear deformation. So all the shear strain will be the same in each plane, but this can be the shear strain can vary through the thickness. Very similar concept as the curvature. So this is also called twisting curvature. So just sometimes easier to understand by mathematics. That's a Z and curvature, and this is the in-plane. So one laminate, okay, one laminate, they can deform, and the strain will be represented by the one directional and two directional and shear. These are three strain, and the uniform and curved, and there is a Z. So this is the function of a Z. Z means each ply, okay, each ply and each ply. So whatever ply dependency will be represented by this Z coordinate. Okay, so this three component can be represented by a vector form, epsilon bar, and this is uniform, epsilon 0. This is all vector. Okay, this curvature is also a vector form, and this is a Z. Z is just a scalar. That's the coordinates in a laminate. Okay, so this one is called in-plane strain. In-plane strain means that is a deform in plane, and curvature K is the curvature. Okay, so the if we count, there's 1, 2, 3. There's another 1, 2, 3. Totally 6 constant deformation values which will describe the deformation of a laminate. Okay. Again, here the most important point is that each ply, we have many plies, many plies. So no matter how many ply we have, don't worry. This we have a z coordinate here. Why only z? Because each ply, no matter how many ply, they will deform together. So there is a no z and no z, because in bending, same thing. They, no matter how many ply, they will deform like that. So for depending on the position, only difference is the there will be a z coordinate. So if there is a z, okay, like the first ply or second ply, third ply, we have a different z, different z1, z2, and z3. So we know the coordinate system, and that's how we can calculate the strain of each ply. Okay, strain of each ply. We have to say this is the function of z, and function of z. Now this arbitrary function of z is just the represented by the z coordinate here. Okay, so please, you know, I know some of you already know about this the behavior, but please keep that in mind. This behavior, this is the most fundamental assumption, but not just more than assumption. This is the behavior of the laminate. So all the composite theory, mechanical theory is based on this observation, this behavior. Okay, so we're gonna drive some equation, and all the equation will call laminate. Okay, laminate theory. The laminate theory is based on this assumption, this observation. Again, each ply deformed together and curved together. So whenever we want to calculate the strain of each ply, we follow this z coordinate here. So short, you can write this one. Well, if you don't feel comfortable with this vector form, is still okay. You just understand this equation, one directional and two directional and shear deformation. And only thing is that this is z. Now, to understand how each ply will deform is that you all you need to do is calculate this 1, 2, 3 and 1, 2, 3. No matter how many ply we have, no matter how many materials layup we have, all you need to do is just calculate this 6. Now, as an example, okay, let's say we have a pipe or composite vessel, tank, and now we have a layer and layer and layer, so many layers, no matter how many layers. They are glued together. the first thing is that they are glued. They glued together. It looks very complicated, right? But the main point is that they all I would like to draw like that. Okay, so many layers like that. And each ply, okay, each ply, we already know this is the first ply and second ply and etc. This is the, we can call, this is the, okay, each, they are glued together. And this can be a laminate. Okay, laminate. Now, our what we like to do is that we like to understand how much. Sorry, it's very inconvenient. So we know that we have a lot of internal load as a pipe or a pressure vessel. We have a lot of load. And no, we know we don't know yet, but let's say this laminate will carried by a lot of load like that. Okay, this will carried by carry a lot of load carried by this laminate, right? We don't know this load, but this is what we can imagine that this they glue together, they laminate. And now this have a lot of ply. This is a lot of ply. I would say ply 1 and ply 2. Well, you can call them as a layer 1, layer 2, and etc. So ply N. Now, how they deform together? There are N times, let's call 100 plies. Then it can be very complicated deformation. But the point here is they are all glued together. So the glued together means that no matter how many laminate we have, their deformation, okay, deformation will be the same. There's epsilon we call 0 times curvature. Curvature means that this will have a bending together. And this is the curvature, and there will be some z coordinate. Z coordinate, this I would say the internal, this coordinate system will be, this is a z, okay, from inside to outside. This is with the z1 and z2 and zn. Each one will have its own coordinate system. So if you want to know this, how much deform ply 1, you know the coordinate, and then you coordinate using this formula. You can have a ply 1 strain. Okay, this is the strain. So all you need to know is that how much laminate, this glued laminate deform, and then how much bending. Bending means this curvature or that curvature. So again, no matter how many ply we have, and all you need to do, we have a 3 in-plane strain and 3 curvature. So how many do we need to know? We need to know only 6. And 6, and then if we place 100, we call multiply Z1, multiply Z2, multiply Z3. So we can have all the strain in each ply. Okay, that's the one example of this laminate theory. So laminate theory is not just for the plate, but can be any composite structures. The point is that each ply, they are deformed together. That's exactly what we studied. So each ply they deform together. Okay, that is the the most. Where is it? Okay. So this one, each ply they glue together, so they deform together, and in plane. And then I didn't say the curvature, but the curvature. So this is the most important. I mean, sounds obvious, but the most important point in the composite materials. Okay, please understand. You don't need to remember all the mathematics, but you just remember by is physical behavior. Okay. Okay. Let's have a 10-minute break. Okay. Now let's consider a very simple materials. Okay, let's say we have a simple bar. We can say this is a bar, and then we apply the force, and we certainly like to know how much the it has a strain. We will have a strain epsilon. Let's call just epsilon. Now, what we know is that this material, we know the stress equal E epsilon. This is a material property. And now another equation is the force. The force is the certainly integration of this stress over the area, right? This is the over the area. The reason we are using the integration is that this can be a laminate or can be any materials. Now here, the most important point we already know is that this strain will deform. No matter how many ply, how many material we have, this strain will be uniform. So this strain will be the same. So if we combine them, then F is the force with the stress E epsilon, but epsilon will be the uniform and like that, and integrations. Now, integration, what does it mean here? The Young's modulus through the thickness can vary. So we cannot, they can vary, but the strain can be uniform like this. So if this is the just one material, we can easily say E times A n times epsilon 0. Okay. And another point here is that we have a bending, like this much bending, bending and the moment. And if we have a bending, this will deform like this, and this will have a R, and this will be the curvature. So by definition, the moment will be certainly the stress times the through thickness and dA, right? Stress times A will be the force, and we need to multiply Z. Usually we have a cross section like this, and we have a stress, and then we multiply Z. This is the stress times A. Okay, and also the sigma equal E epsilon. Now epsilon here is the since it's a curved, simply we can say that Z epsilon Z curvature, right? Z curvature. Well, this is the pretty much the level of strength of a material or mechanics compared on the strength of material undergraduate level. So we have this. So this M, we put them together for here and here. Then moment will be a E epsilon and zk, and curvature here, and we have one G here, and there's another Z here, so G square and dA. Now the curvature is the constant, so E epsilon zk epsilon Z, I mean the G square and dA and curvature. So here usually this is the force we apply, and this is the curvature we like to have. Okay, and the strain we assume this one and this one. So if we combine them, you can see that epsilon will be in general epsilon 0 plus zk, and epsilon Z and K is the given here. So flow is like the this is a given. Okay, this is the given load, and using if we know this one and this one, and we can calculate the epsilon 0 and K, and then we get this much the strain, and once we know the strain, we can calculate the stress for each position. Okay, that is the flow, and so here the point is the what is the E? This is a stiffness. What is the A? A means that the total cross-sectional information, and here is the same thing. E is the Young's modulus, and Z. So in strength materials, we can say this is the EI. I means the bending stiffness. Okay, E and K. So if we put them together as equations, one equations. Okay, so this is the A material. We have a force. We have a bending moment, and this can be now can be many material. Now, how much it extended, and how much it curved, and now is the expressed by the F and M equal. This is the EA, times epsilon, and now this is EI and K. And now this can be in a matrix form, F and M times EA. Well, here we can EI. Now you can say that epsilon 0 and curvature. Okay. And please pay attention the meaning of this one. This is the stiffness of E of each ply and each thickness. And this is the each stiffness and the locations. And now this can be extended to a plate, not just the one direction, but now is the extended to a plate. So we can have this load and this load and this shear load. And even for the bending, we can have this bending and this bending and this bending, and then this curvature. So here in general, this is now instead of F, we have a N1 and N2 and shear N6, and in the bending we call M1 and M2 and M6. And now this 0, what does it mean 0? 0 means that this axial load and this curvature, sometimes, let's say, depending on the layup sequence, this F, just on the F, this may have a deformation. Just the F and curvature or curvature F can be coupled. So this can be some value. So this can be a non-zero value. So let's call this just for convenience. Let's call F and M. Let's call this is the A, and this is a D, and this is called B, and there's always a symmetry and B, and this is the epsilon 0 and curvature. And now again, this F is not just one value. F now instead of F, we are using the N because of many reasons. This is a load per unit length. So N, but N is not just the one direction. We have this one and this one and this one. And moment is the same thing. So this can be a rather than one value, this can be a matrix. And rather than one value, we can have a 1, 0 direction and 2 directional strain and shear direction. And curvature is the same thing. So even this ABD, this can be a matrix. Okay, so N is the 3, and M is a 3, and this is a 3 and 3. So so this is a very famous equation, ABD matrix. ABD matrix. Try to understand that A, B, D, where did they come from? All the information regarding the material property of a stiffness of each ply, Young's modulus, and the locations. A or I means that this location, layup sequence. So material property and sequence give us the ABD. You can always refer to other reference to get this, how we calculate the ABD from each ply and from each sequence. But the point here is that this is the given, This will be given. And then now you can calculate this one because we know this layup sequence. Okay, so this is the final form of the laminate theory. The most important concept and equation, we have to understand that. Okay, this is the laminate. You can call A, B, D. Of course, the main question is the how calculate the ABD, but don't worry too much. That will be calculated. But more important point is that this is the forces. This is okay. Now I'm going to use this slide. See, we have a one-dimensional bar. We have a P. I use the F, but the force and epsilon is the relate to EA. This is very typical isotropic, and the bending E moment and curvature EI. So EA and EI are the stiffness. Okay, and then we have a. I don't mean to just skip that, but I just like to emphasize the final concept of the equations that this one, this laminate, and this is the definition of in-plane load and stress and the moment and the stress times Z. And then each will have a, it looks very complicated, but the point here is that this is the final form. You know, this is the final form, ABD. And with this, if this is the stiffness matrix. Once we know this one, that means if we apply the force, we can calculate this strain. Once we know the strain, then what we can do is they come to this equation, epsilon K, and this we know, and this is the strain. And now we can calculate all the stresses in each plane from the given this load. Okay, so stepwise, this is the first step. This is given, and then we calculate this the second, and then come to here that we calculate the strain, and then we calculate the stresses of each plane. Now here, to do so, to follow this, of course, we need to have this ABD matrix. ABD matrix, how do we calculate that? Okay, we have a very similar procedure. This A is like a Young's modulus integration, Young's modulus and position integration, Young's modulus and position integration. This is the ABD matrix. Okay, so just to try to please understand the concept. This is the material property and the layup sequence, and then this will be calculated by the program, and then if you know the NM, and then you calculate, you know, the strain, the laminate deformation, and once you know the laminate deformation, this the third step you will understand the ply and the ply stress. This is the very typical procedures of the laminations. So no matter how the composite material you have, this is always the the step we need to follow. Okay, so this is the classical laminate theory. Well, I certainly skip many steps, understanding the stress strain curve like this. I skip this many steps, but I like to go top down rather than bottom up. Top down, we remember this flow and concept. And then how do we calculate the ABD? Once we have an ABD, we can get this one, okay? Again, the purpose is that I just like to give you overall very basic flow. And then I will do it again from the very beginning, step by step. Again, the purpose is that rather than just go through one equation by equation, you can easily get lost. So I just want to give an overview, and then I will go step by step, starting from each price stiffness, and then deformation condition, and the definition of the load in plane load the moment, and this is a final form. And then we can get the ABD. So in backward, once we have the NM, we calculate the epsilon and K, and then come to here, and we calculate the price strain and price stress. Once we know each price stress, then we can tell, oh, this ply will fail, this ply will break, and we can tell, we can predict many things because we know each ply has how much the strength it has. Okay, that is the flow. So we didn't touch much equation, but conceptually is the step. We mainly went through the steps from extension of isotropic materials and extended to composite materials. Only difference will be here, instead of I'm gonna say rewrite here. Here, this is a well known. I'm sure you know this one, but this equation again we can rewrite. This is the P and M equal EA and EI and 0, 0, and epsilon and curvature, right? I will say epsilon 0 here because it's a uniform. This is the uniform strain, like this is epsilon 0, and because of a moment, this will have a curvature like this. So this is the curvature. So from here, this is the load we apply. We can have a epsilon 0 and curvature, how much the strain and curvature. And to calculate this one, we need to know this material and then a sequence, and this material is sequence. And there can be some another term here, And as you can see, this is very similar to what we are trying to arrive. We are trying to reach the ABD matrix for the composite materials like this. Okay, so I like to give you an idea that what we are trying to reach is just the extension of this equation for the isotropic to our composites. And then to do so, we need to take a step by step. Even to reach this one, we skip many things, but we start with the sigma equal E epsilon. This is the basic material properties, right? And this E is a epsilon 0 plus through the thickness and Z and K. So again, once we know the epsilon 0 and K, we got this, and then we got that, and then epsilon, and then we get the stress. So stress means this guy, each ply, each positions of stress. Each position is sometimes compression, sometimes tension. So once we have this one, then we have a failure. Okay, this is what we already know in undergraduate, strength of materials. And now what we try to do for the composite laminate, whether it's a pressure vessel tank, whether it is the airplane, we're gonna have is this ABD matrix. But I'm trying to say that this is nothing new, and this can be considered as an extension of the isotropic relations. Okay, so don't worry too much. Oh, this looks very complicated, but the the first step how to calculate the ABD is the we're gonna touch that. The program will tell us. Don't worry, and this is the one we're gonna reach. And of course we're gonna use the Excel program to calculate how to calculate the ABD and how to calculate the epsilon zero and curvature and how to calculate the whatever things. So let's say we have a 3 and 3. So this gonna be later you're gonna have a matrix, and this gonna be a D matrix, and this gonna be a B matrix, as we already mentioned. Okay, and then we're gonna have 3 force and 3 bending moments, and we're gonna calculate this strain and curvature. So let's say I just give you an idea, nothing new, but this is the just some number we're gonna calculate. Let's say we calculate how, again, don't worry, we're gonna learn how to calculate this ABD matrix. Now this is the force 1, 2, 3 and the moment 1, 2, 3. Well, how we can, this is gonna be a given, okay? This is gonna be a given, and also we just enter some value. Well, let's just give us some value. Let's say this is gonna be 1 and this can be a 0 and some value, you know, whatever load and whatever things. Now the point is that how we calculate this guy, and this guy will be simply matrix inverse. And how we calculate this one? Matrix inverse, we have to inverse this matrix, right? And then this guy, we have to multiply. Well, don't worry, we don't know much about these things. We will learn as well. So this M inverse and transverse and load. I can't, how come it doesn't give us the value? transpose, we have to inverse. No need to transpose. Okay, well, again, this is just a constant value which will be calculated from theory, and this is a load. Now, how can you calculate the strain? This strain is usually the output, and in red, and this is gonna be input at the load, and I'm gonna use the blue color, and this is the theory. So again, let's say this guy is this three guy is the N, this three guy is the M, this three guy is the epsilon 0, and this three guy is the curvature, and this 3 by 3 is the A and D and B and B. This is exactly what we already derived. Well, one missing part is how we calculate this ABD. This is the one we're gonna learn that. Now, epsilon 0 and curvature is given by like the A, B, BD equal N and M. How we calculate this epsilon 0 and curvature? This one is simply the the inverse, right? Inverse times the N and M. That's exactly what I wrote here. See the M inverse of this guy, and then M multiply. Inverse and multiply, we got this one. So again, this will be given, the load will be given. Okay, load will be given. And here we have many ply. And we're gonna have a load N1, and this is the load. And how much you will deform? Deformation. This deformation will be here. So all the layup sequence will give us this one, and then if we know the load, we can calculate this the strain. Okay, this is a classical laminate theory, and then what we're gonna do is that how we drive this ABD matrix. Okay, that will be the cover next class. Okay, but please review what we have cover today. I just want to give you some get you ready for next step. So this is the just an overview, so that we can take a step in detail. Okay, today I'm gonna close a class at this point. We didn't cover much, but again, this the most important steps in understanding the composite theory. So and also we're gonna have a simple Excel programming. More important, we need understanding all the steps. Okay, so this I just simply share with you. This is the final equations we gonna reach. Okay, so today please get yourself to be familiar with these formulations. Okay, I know some of you already know this, but some this formula is new to you. But just try to understand the how we reach this equation. Okay, well, thank you, and this is all we like to cover today. Okay, let's keep in touch through Kato, and then see you next week. Thank you. Bye.